today's seminar. The speaker is Professor Yusuke from here. I have concrete introduction to all the super QFTs with no known Lagrangians. Please.
Thank you. So today I'd like to introduce you to four-dimensional supersymmetric QFTs without any known Lagrangians. Let me first say that today I say something big but very vague, and which might be a bit crazy. So I'm not sure if I'm old enough to do such kind of things, which is usually only allowed for elderly professors who went nuts. But so let me try anyway. So today's topic is four-dimensional quantum field theories without any known Lagrangians. Of course, I needed to add this adjective known in it because someday we might find a Lagrangian for the theories which I'm going to talk about. So you need to keep in mind that, but let me try to explain the concept, assuming that we will not find any Lagrangian description for that kind of theory. So this is what we usually do when we study quantum field theory. We start from basically free theory, which consists of gauge fields and some matter fields. And that theory, as you flow down the renormalization group, that becomes more and more interacting, and it becomes even more strongly coupled, and eventually you lose the control. So that's what we usually analyze if you are interested in strongly coupled quantum field theory. But my question is whether you really need this first part of starting from a free theory. Do you really need it? Maybe it's not necessary, or maybe it's possible that there is no free descriptions from which you start. So that's my question I'd like to pose today.
You mean by free?
Weekly coupled phase. So we usually assume that there is some asymptotically free thing in UV, but I'm wondering whether it's really necessary. And I think there is a counterexample to that common conception. So that's what I'm going to, I'd like to try to explain today. Right, so maybe there might not be such things if you consider a general enough quantum field theory in 4 dimensions. So when I say non-Lagrangian, I mean that it doesn't currently have a Lagrangian to be used in the path integral description of the theory, which becomes, in the infrared, that theory, which we'd like to study. Of course, there's a Hamiltonian framework. I'm still keeping the general principle of quantum mechanics. Quantum field theory is just an infinite degrees freedom quantum mechanics, so there's a Hilbert space of states, and there are operators acting on it, but there might be no Lagrangian description for that theory. So that's the kind of thing I'd like to consider today. And honestly speaking, saying that it doesn't currently have a Lagrangian might not be a very good idea. In fact, I believe that some of those theories don't have any Lagrangian description, and I don't think Lagrangians for those theories would ever emerge in the future. I mean, who told you that every system should have a Lagrangian description to start with, right? When did you learn that? You are just basically following the dogma you learned from quantum field theory textbooks. That's not any different from religious fanatics believing everything in the holy books, right? So what I want to say is repent. So you need to forget everything you learned in your textbooks. So in Japanese, 悔い改めよ, right? The new way of thinking about QFT is coming. You should forget about the old ways, right? So this is your first step into the new way, into the QFT, right? So, the ordinary approach to any QFT problem is this. You pick gauge fields of your choice, you add matter fields, and you add some interactions, and then you start analyzing the system. That's what we always do. It often becomes strongly coupled in the IR, but somehow, almost always, we assume that it becomes very, very weakly coupled or free in the ultraviolet. But it doesn't have to be free in the ultraviolet, right? All the necessary thing is that it just needs to be a consistent quantum field theory in the ultraviolet. So you need to remember that ultraviolet completion we often talk about in any QFT doesn't mean that in the ultraviolet the theory becomes almost free. These are two different concepts.
So what do you mean UV and IR without path integral formalism?
Well, there's a scale, right? If you measure a two-point function which are separated in a very short distance, that's UV. If you measure things in a very long distance, that's the IR. So the kind of space-time's RG flow is still there, even though you don't have any Lagrangian description. So if I say, if the word non-Lagrangian theories are a bit too extreme, you could think of non-Lagrangian theories I'm talking about as some kind of non-trivial UV fixed points which can replace free fields. So free fields are not the only ingredient. That's what I want to say today. So this is, again, a picture of what we usually do. So we take gauge field, some matter field, and put some interactions. So these small box in the matter sector here symbolizes gauge current to which gauge field couples. So this matter field also has a current to which this gauge sector couple. And of course, there can be some interactions between matter fields themselves. They are basically 3-point or 4-point couplings of the matter fields. So there can be many things. Right? And if you change the scale, you measure the system, the coupling constants change. So in the IR, the couplings would become stronger. So I depict the strongness of the coupling by the thickness of the line. And instead, if you go to the UV, couplings often become smaller, right? And as you go to the UV, eventually you get to a completely decoupled system where you have zero coupling gauge field and zero coupling free fields. That's what we usually do. But you need to remember that the free field is just one example of UV fixed point. So I just rewrote free field as a free UV fixed point, right? So you can replace free field, a free UV fixed point by whatever non-trivial UV fixed points. So you can start from zero coupling gauge sector, zero coupling free UV fixed point, but together with non-trivial UV fixed points, which can be interacting. So this is the same thing. I just dropped the word UV fixed points. So we can start from this combination and start adding interaction to it. So non-Lagrangian theory can also have some flavor current to which the gauge current can couple, and you can also introduce a interaction among non-Lagrangian theories, which are given by the products of operator of this and the operator of that. Or you can consider coupling of the free field here and non-Lagrangian theory.
Excuse me.
Yeah.
I don't understand the connection between relation between Lagrangian theory or non-Lagrangian theory and free or interacting.
Well, there is not really a connection. I'm just I'm just saying that in the usual Lagrangian field theory, you start from known fields, right? Fermion fields and boson fields. I'm just referring to them as free fields in the ultraviolet. Yeah. The other non-Lagrangian theories won't be free in the ultraviolet. By free, I mean just standard Fermion fields or boson fields, scalar boson fields.
You think that if the theory goes really the non-trivial fixed point, that cannot be expressed in terms of Lagrangian?
That's fine. Well, if you have a Lagrangian, which then floats to a strongly coupled theory,
Right.
then I consider this theory still Lagrangian theory. I'm just talking about the non-strongly coupled fixed point to which no Lagrangian description can flow into.
Okay, so the previous slide and this slide is not equivalent, but you further
This one and that one?
no, this one and the next one.
Next one?
Yeah.
No, these are the same thing. Maybe my
Oh, sorry, because UV fixed point,
right.
not the infrared.
No. Right. That's the important point. I'm talking about non-trivial UV strongly coupled fixed point. That's the difference.
That theory is you say non-Lagrangian.
Right. So maybe I shouldn't have used the word non-Lagrangian at all. I'm just talking about non-trivial UV fixed points.
Can you parameterize such a fixed point theory without using Lagrangian?
There are some known ones. Yes.
You mean you can parameterize the theory in terms of Hamiltonian?
Yes. There are sets of operators.
Yeah.
So, well, QFT, abstractly speaking, is just given by a set of correlation functions satisfying certain properties.
Yeah.
That's what I'm going to discuss. So, starting from mixture of free fields and interacting UV fixed point, we can add gauge interactions or interactions among free fields and non-Lagrangian theory or among non-Lagrangian theories themselves. You can start going down the RG flow again. Then it can become strongly coupled again, right? So compare this to the more traditional setup where you just start from free fields and gauge fields which become strong in the infrared. Instead, a more general situation is that you start from a gauge sector, free field, and some other non-trivial UV fixed points whose couplings among themselves become even stronger in the infrared. So I'm just saying that you don't have to assume that everything becomes weakly coupled in the UV. So let me say this again. Ordinary approach to any QFT problem was this. Pick gauge fields of your choice, pick matter fields, pick interactions among them, and analyze the system. I'm just suggesting a very small change. So the first step is the same. Pick gauge fields of your choice, pick matter fields, which can be either free or these non-trivial UV fixed points or non-Lagrangian theories, and pick interactions among these two guys in various ways. And you analyze the system. So please think of non-Lagrangian theories as new basic ingredients like in QFT, almost as important as free fields, right? So learning free fields, learning the properties of the free fields is a very, very important thing we all did, right? But there are similar basic ingredients of QFTs which we haven't learned so much. So this is surely an important thing, I think. So again, I'm just repeating the most important thing, right? So pick gauge fields of your choice, pick matter fields which can be either free or non-trivial UV fixed points, and pick interactions. So you can consider this combination as some semi-Lagrangian theory, because some part of it is still given by a Lagrangian. I mean, the gauge field part is given by a Lagrangian, but some of the matter content is non-Lagrangian. But the interactions between them can still be written as the product of the operators among non-Lagrangian systems, etc., etc. So This is the system I'd like to sell to you, right?
So can non-Lagrangian theory have gauge field?
That's a ill-defined question because
Ill-defined.
yeah, I mean, what do you mean by having a gauge field in it?
Well, if you define non-Lagrangian theory by correlation functions,
Right.
the question is, can we include the gauge fields in that correlation function?
Well, you can add,
No,
certainly
not that
add.
one, not that one, but the gauge theory. So suppose that you drop out all the interaction between these.
Right,
samples.
right.
Can we still have a gauge field inside this fixed point?
So when I say correlation functions, I only talk about gauge invariant
Gauge
correlation
invariant.
functions. Right. Yeah.
So that implicitly assumes that all gauge interactions become strong
Right. Yeah. Well, I think the correct statement is that there are just correlation functions, which I mean operators can have spins, yes, but you just don't know whether you have a gauge field or not. That's not a well-defined question. When you have a Lagrangian, you can say that there are certain non-gauge invariant fields, but in general,
some operators may have an index which is the same as the gauge field, Lorentz index,
right.
something new.
Well, current has one vector index, yeah, but that's not gauge fields, right?
Right.
So, yeah. So you need to think again if you have any question about QFT, because the standard way to formulate a question sometimes doesn't apply to non-Lagrangian theories. So you need to be careful.
So the ingredients of these correlation functions are not necessarily the particles, or you mean just operators.
Just operators.
Yeah.
You just have composite operators whose origin you don't know. So that's the non-Lagrangian theory. So this is my subjective picture of this whole space of QFTs. There are some free fields, there are some Lagrangian theories, but there are tons of non-Lagrangian and semi-Lagrangian theories. Of course, there are very good reasons why we want to study Lagrangian theories, because standard model is a Lagrangian theory. So it's okay for those of you who are phenomenologists to study just Lagrangian theories. But if you are just interested in the properties of QFTs, if you don't study non-Lagrangian theories, you are just artificially restricting your attention to a very, very small corner of the vast possibility you can study. So, how can we study them? Unfortunately, no general framework is yet available. That's one reason why it's so interesting, by the way. And thankfully, n equals 2 supersymmetric ones are rather tractable because it has lots of supersymmetry and there are many techniques to study it without using the Lagrangian. So there are many n equals 2 examples I know. The first one was found in 1996, around 15 years ago, by Minahan and Nishansky, and they are called Yen theories. And nothing happened almost for 10 years. And Argyres and Seiberg found that Minahan and Nishansky's theory is very important if you consider duality of just Lagrangian theories. And then, soon afterwards, Argyres and his student Wittig found many other examples of Lagrangian theories, and then Gaiotto came to the business, and there are tons more constructed. Because of the time I have, I can only talk about the very first developments of this story, but if you're interested, you can always ask me. Right. So, of course, you would ask, what about n equals 1 supersymmetric theory, or how about non-supersymmetric non-Lagrangian theories? Are there such things? Honestly, I just don't know. We don't have any technique to analyze those less supersymmetric cases. But one thing I should add is that you can just add n equals 1 or n equals 0 gauge sector or free fields to n equals 2 non-Lagrangian theories. Therefore, the total system is still semi-Lagrangian with less supersymmetry than n equals 2. So definitely there are semi-Lagrangian less supersymmetric theories which you can study. As an example, I discuss only this theory found by Minahan and Jansky. And a bit of preparation is necessary because we need to start from n equals 2 version of supersymmetric QCD. I introduce only a very basic aspect of it. So this is the matter content of this theory as n equals 1 gauge theory. So n equals 2 supersymmetric SUNC gauge theory with nf flavors have the following matter content. You have n equals 1 SUNC vector multiplet. You have SUNC R-joint chiral multiplet. So these two combine into n equals 2 vector multiplet. You also have quark fields, and we introduce NF of them. So you have NF fundamental SUNC chiral fields, Q, and the same number of anti-fundamental chiral fields. So this is the standard matter content. And in order to make it n equals 2 supersymmetric, you need to add a superpotential of the form Q phi Q twiddle with a fixed coefficient. Otherwise, the theory is just n equals 1. The important thing is that the one loop beta function of this theory is given by 2nc minus nf. So if you have a number of flavors less than 2nc, you have a asymptotically free theory. If you have nf equals exactly 2nc, you have a semi-classically conformal theory. And if you try to add more than that, the theory is infrared free. So this is the standard cascade of theories. You can start from SU2 with 4 flavors, which has beta function 0. As I just told you, the beta function, one loop beta function is 2nc minus nf. And you can add a mass to one of the quark fields, and you can flow down to SU2 gauge field theory, this flavors. You can repeat it to go down to n equals 2 gauge theory with 2 flavors, or 1 flavor, or just pure n equals 2 gauge theory. So I'm afraid most of you think that this cascade terminates at this point. But that's not the case. It is known that there is a UV fixed point, which is basically like SU2 with 6 flavors, but which after a mass deformation flows down to SU2 with 4 flavors. So this is clearly non-Lagrangian or non-trivial UV fixed points. So this Minahan and Jansky's E6 theory is n equals 2 supersymmetric, has E6 flavor symmetry, and it has no Lagrangian description.
So what do you mean by mass deforming to this theory close to the Hongo invariant theory?
Well, you can just add the master.
Mass term?
So adding a master in the standard gauge theory means adding this term in the Lagrangian, right? MQQ twiddle. This QQ twiddle is a dimension 2 operator. And in the strongly coupled case, writing it as QQ twiddle doesn't make much sense. So what you do, in fact, is to add a dimension 2 operator with a certain coefficient. That's the mass deformation in the general case sense. So what I'm saying in this line is that this Minahan and Jansky's theory has tons of meson fields which have dimension 2, which cannot be written as a quadratic combination of something more elementary. So you just have meson fields. But you can still add a term, linear meson, which is a relevant deformation. Therefore, this flows down to something else. That
in what sense they discover that theory? So you said that there's no Lagrangian.
right.
So in what sense they discover? You
So
mean one can compute many correlation functions in that set?
Right, right. I'm going to explain it from a modern point of view. Yeah. Right. And in this case, the absence of any Lagrangian description in a naive sense can be argued in a very straightforward way. Because any n equals 2 supersymmetric theory is given by something similar to what I just told you. You just pick a gauge group and a quark field, and the only thing you can add is a superpotential of the form q phi q twiddle with some fixed coefficient. That's the only possible n equals 2 Lagrangian. You can study its flavor symmetry. Flavor symmetry of this system can only be SU or SO or SP. You can never get E-type flavor symmetry from n equals 2 Lagrangian theory. So I'm pretty sure that this guy doesn't have any Lagrangian. But of course, your question is, how do we know such a thing exists? If you accept that string theory exists as a consistent quantum theory, then you can just use F theory 7 brane and put the B3 brane close to it, and that's Minahan-Michansky V6 theory. But I don't like to use a string theory in this talk. I just want to use four-dimensional quantum field theory to argue that there is such a non-Lagrangian theory. But you need more efforts to do that. So I'd like to tell you a bit about the construction of this E6 theory. By the way, this is not the original way Minahan and Michansky found that theory. This is based on the work by Arguelles and Seiberg. Right. So I already told you that n equals to SQCD with NC color and NF flavors when NF is 2NC is semi-classically superconformal, by which I mean that the one loop beta function vanishes. And due to the big holomorphy in the theory, the system is believed to be non-perturbatively superconformal. So the combination 4 pi I over g squared plus theta is exactly marginal. So you can change the value of g from very weakly coupled point to a very strongly coupled value. So you can ask, what happens if you send g to infinity? The answer is, well, that depends on the theta angle. The outcome depends on the theta. But general theta angle is rather complicated, so let's just consider CP invariant cases where theta is 0 or pi. The simpler case is when theta is 0, and the reason why we can study such strongly coupled system is that in the case of n equals 2 gauge theory, there is a technique called Seiberg-Witten curve, which tells us not only all of the masses of the BPS particles, but also all of the numbers of particles, I mean the types. How many types of particles exist in the system? In the original paper by Seiberg-Witten, they only discussed how to get all of the masses and how to read off the number of or types of particles in the system was not known in 1994, but in the last 20 years, the technique developed. And now, with this data, you can get basically the full spectrum of the supersymmetric particles in the system. So that's the method. I'm not going to explain to you in detail how it's done, but the important thing is this. When theta angle is 0, we can study what happens to this auxiliary Seiberg-Witten curve when g is sent to infinity. What happens is that the Seiberg-Witten curve at coupling constant g is exactly the same as the Seiberg-Witten curve at coupling constant g prime, which is inversely proportional to g. So when g is extremely strongly coupled, in the dual frame, you have almost free gauge multiplet. So that's the statement about the Seiberg-Witten curve. But as I told you, from the Seiberg-Witten curve, you can read off all of the masses and numbers of particles in it. Therefore, it's quite likely, I believe, that this n equals to SQCD with this number of colors and flavors at coupling G is equal to the same theory with inverse coupling constant. But this is only for theta equals 0.
What do you mean by saying that one can read off the number of fields? Did you say fields or
The number of fields, yeah.
You already said in 2MC flavors. So it seems that the number of fields are already fixed.
Yeah, on this side it's fixed.
Yeah.
But you need to see how many particles there are in the strongly coupled limit, right? Without any Lagrangian.
Do you mean the light degrees of freedom?
Right.
Okay.
The light supersymmetric degrees of freedom can be determined just by looking at the curve. So what you do is to first write down the curve in the weakly coupled case and tune the coupling to very, very strongly one. So you lose the Lagrangian because it's very strongly coupled. But still you can count how many fields there are, light degrees of freedom there are. Yeah. Well, it doesn't have to be like that. As far as it's BPS and 1/2 supersymmetric, then you can determine the number of states. Yeah. When theta is pi, the behavior is rather different. It happens that when you take the coupling G to very, very large value, you don't get the Seiberg-Witten curve with inverse coupling. It is not the same as theta equals 0. Instead, what you find is that in the G goes to infinity limit, you find weakly coupled SU2 gauge group. We start from SUN-ish theory, but in the strongly coupled limit, you find there are SU2 gauge bosons coupled to one flavor of SU2, and you have some mess. So that's the thing you find by analyzing the Seiberg-Witten curve. So it is then likely that if you start from this super QCD at theta angle set to pi and tune the coupling to a very, very large value, you get SU2 gauge theory at inverse coupling with one flavor of quarks and a mess. So let me say that using a picture, which might be a bit more understandable the words. So we start from this system. You have gauge sector and matter sector, right? You have SUNC current to which the gauge field couples, right? In addition, you have the baryon number current of the system and also SU2NC flavor current. That's the system.
This is Lagrangian theory.
This is still a Lagrangian theory, and this is starting point, and G is very, very small. So I'm going to crank up the coupling constant. So it slowly, the system becomes complicated when G becomes close to 1, and around G equals 1, everything becomes murkier, mistier. But one thing is still true. There is a flavor symmetry current. There's an gauge invariant operator which does that, right? And, well, if you tune the coupling further, you get something else behind the curtain. And if you further go to a very, very big value of G, which is a very, very small value of G prime, you get a different set of system, which is a semi-Lagrangian theory I told you at the beginning of the talk. So you have a SU2 gauge field, and one flavor of SU2, and some non-Lagrangian theory. You can make the coupling even smaller, and you can go to a completely strongly coupled limit in the original theory, which corresponds to a zero coupling limit of this theory. In this way, you extract a certain strange theory, which doesn't have any Lagrangian. So we isolated a strange mess with SU2F flavor symmetry and SU2MC flavor symmetry. This SU2F flavor symmetry came from its coupling to the SU2 vector field. So gauge symmetry became zero coupling. Therefore, the gauge symmetry became a flavor symmetry. So in this way, you can construct a mess, which is a non-Lagrangian theory, for any NC. Not only for NC equals 3, but when NC happens to be 3, something special happens. So this SU2 and SU6 combines into a bigger flavor symmetry, which is E6. This is the Minahan-Michalski's E6 theory.
So how do you know that there is no UV alternative dual theory which flows into this theory? This is UV.
Well, this is UV
yeah,
fixed
yeah.
point.
Okay. Okay.
Well,
It's impossible.
yeah, but honestly, I don't know whether there is a Lagrangian description which can flow down to this thing. But I'm just saying that this is this doesn't have any Lagrangian so far, but still you can use it to study semi-Lagrangian theory, right? So that, independent of whether this theory really has a Lagrangian or not, you can enlarge the type of QFT you can consider by using this as a starting point in the ultraviolet. So,
Excuse me.
right.
But to obtain this picture, you put the original gauge coupling to 0
To infinity.
to infinity.
Right, which corresponds to the dual coupling goes to 0.
But that limit corresponds to the direction go to the UV?
No,
in the
no, it's a superconformal theory.
Yes, yes, yes.
So the coupling is not related to the scale.
Yeah, but you said that this is the UV completion of that n equal to.
No, I'm not saying that. No.
This theory itself is still a fixed point.
Right. At every stage of these pictures, everything is conformal.
I see. So you just to take,
Right. So
take
this is exactly marginal coupling you can tune.
yeah.
So I'm not going up the energy scale in this sequence.
Oh, I'm
of pictures.
confused because you said that you mentioned that sequence.
Right.
Between the cell.
That sequence is not related to this
Okay.
procedure of extracting a non-Lagrangian theory. I used this to tell you that indeed such a theory exists. So you might wonder how to compute the correlation function in the theory, right? So computing 3-point functions is very hard, but you can compute 2-point functions. So that uses this duality. So remember, SU3 gauge coupling is exactly marginal. That's why I could change the value of the coupling continuously. On the dual side too, SU2 gauge coupling is exactly marginal. That's why I could change the dual coupling continuously. So this means that the beta function, one-loop beta function of this system is 0. How to compute the one-loop beta function of non-Lagrangian theory? So I use this as an input. So we all know that n equals SU2 with 4 flavors has 0 one-loop beta function. In this setup, we still have SU2 gauge field, and we have just one flavor of quarks, and you have something strange there. But still, one-loop beta function of the total system is 0, right? This means that the 2-point function of the current of this mysterious theory should be just 3 times the 2-point function of the free theory. So in this way, you get the correlation function of J mu A, J mu B of this Minahan-Michalski theory to be 3 times delta AB times something which guarantees the Lorentz invariance and such. So this is how you compute the correlation function.
Of the gauge current?
That's a flavor current. There's no gauge field. I mean, it's gauge current, but we take the limit where the dual gauge coupling is 0. So it becomes a flavor current. Right. You see, so this flavor current has this normalization 3. What about the other 2-point function? So we start from this setup, right? In the original case, this is a standard current of high-outlet, so you can compute. Basically, from the point of view of the flavor symmetry, there are just NC fundamental fields. Therefore, the current correlator here is just given by NC. There is a non-renormalization theorem, thanks to the supersymmetry, so it doesn't depend on the coupling constant. So you go to this mystic region, comes back to the dual region, but the coupling constant doesn't change. So at the end of the day, you get NC as the coefficient of the 2-point function. In the particular case of NC equals 3, this happens to be 3, which are the same as the 3 I obtained before, right? So that's one confirmation that the in the Wiener-Hamilton-Jansky theory, this SU2 flavor symmetry and the SU6 flavor symmetry can be both subgroups of a bigger flavor symmetry group, which is E6. Of course, this does not prove that these two flavor symmetry groups can be enhanced to E6, but there are other evidence that indeed the symmetry enhances. You can also study what kind of other chiral operators exist.
In the previous slide, the superscript A for SU2 is SU2 adjoint.
Right.
And right one is SU6 adjoint.
Indeed.
If the symmetry is enhanced up to E6,
Right.
SU2 and SU6 current has some non-trivial or non-vanishing.
No, they are, I mean, there's a subgroup of the form SU2 times SU6 within E6. They are orthogonal in it. Yeah.
Because there's a chronic.
Right. Yeah. Well, you can just open Solansky to find a list of subgroups. You can also study chiral operators. Again, you use the duality to track what happens to the operator. So let's start again from this Lagrangian system. And you have two operators, well, there are more operators, but let's consider an operator constructed solely from vector multiplet field. So you can consider trace of phi squared or trace of phi cubed. If you consider trace of phi to the fourth, that is in fact the square of this thing, etc. So the independent operators are just U2 and U3. Again, the number of operators cannot change thanks to the non-renormalization theorem in the n equals to SUSY theory. So you can go to a dual region, and SU2 gauge theory has this trace phi squared, but you lose trace phi cubed in this part. Now, this is a free field, so you cannot have operator constructed from the vector multiplet side. So it means that the dimension 3 field should belong to this non-Lagrangian mess. So in this way, you can confirm that this non-Lagrangian theory has a trace phi cubed-like operator, U of dimension 3. If this is a gauge theory, I can introduce a dimension 1 field which is gauge dependent and write this U as gauge invariant combination of something more elementary, but that doesn't seem to be possible. So you just have U of dimension 3. And all other BPS and chiral operators can be determined in this way using the duality. So we already know the full set of chiral operators of the Wiener-Hamilton-Jansky theory. So what does this U field related to this power of the theory? So you can start from inheritance theory and add this term linear in liaison, which I call the master because it's a dimension 2 deformation.
And to what?
Huh?
To what?
To this theory.
To more concrete. So you have only correlation functions?
Yeah.
So do you add this term to the correlation function?
Yeah.
If you don't have a Lagrangian, what do you mean add a term to something?
What?
I'm just confused because if you already usually I have in mind if you add a term to something, it is a Lagrangian.
You are so old-fashioned.
Yeah. That's why I'm asking.
What are you talking about?
You only have correlation functions.
In terms of the correlation functions,
Yeah.
deformation by an addition to the Lagrangian, well, we don't have a Lagrangian, means that new deformed correlator is given by O1, O2, O3 is the addition of exponential of this deformation term, some operator integrated over the spacetime. This is the way you generalize the concept of adding a term to the Lagrangian if you don't have the Lagrangian.
So does that operator, is that operator consist of the original operators? I mean, already existing operator?
Yeah. This needs to be one of the operators you can add to the correlation functions.
So I'm just confused. Then it seems that the information in the second one is already included in the full set of possible correlation functions in the original theory.
Right. That's the same with what we always do with Lagrangian theory, right? Everything in the Lagrangian theory can be computed from the weak contraction of the free fields at the end of the day. This is no different from that. Right? In the perturbative evaluation of the correlation function, what you do is to bring down the interaction terms in the Lagrangian, right, and expand the exponential term by term and evaluate the resulting free correlator by the weak contraction, right? So when you deform the non-Lagrangian theory, you don't have the weak contraction. Instead, you just bring down various operators, which is string interacting, but you evaluate that, assuming that you know the full set of correlation functions.
So, let's the other way. So, there's the set of all correlation functions change before and after the modification.
Not really. I mean,
but then the theory is the same.
No, the values are different. You can ask exactly the same question to the case of Lagrangian theory.
Yep.
Yeah, then you get into a trouble, right? You start from a standard 3 theory. I mean, just consider 5 to the 4th theory with just one boson. You start from 3 theory, include 5 to the 4th here, and the way you compute the correlation function in the new theory is to bring down 5 to the 4th, and perform the weak contraction, which is a completely free field operation. There's absolutely no difference.
Okay, I understand.
So that's what I mean by the mass deformation. And that brings me down to SU2 with 4 flavors. And the fact is that you can give a wave to this adjoint to break the SU2 gauge theory to U1 gauge theory. If you give a wave to a triplet, SU2 breaks to U1. That's the standard Polyakov model, right? So,
Is it possible, is it possible to define all the correlation functions by using the duality you use?
Well, for the supersymmetric correlation functions, yes, we can do that.
In principle?
In principle, it's not done yet. We just determined.
So you illustrate the 2-point function case.
Right.
But the computation for higher correlation functions seems much more involved.
Right. Yeah, I'm not. Nobody is has succeeded in doing that yet. Yeah, that's something we need to do.
So it's possible to say that such kind of coercion function can be in principle definable.
Yeah. Why? Why not? I mean, at least in this Minahan-Nishansky's case, if you don't believe in the existence of these correlation functions, you are just implying that you don't believe the consistency of string theory. That's fine. You can stop doing string theory.
It's related to the consistency of string theory.
I mean, because this Minahan-Nishansky theory is just a D3 brane probing a E6 type 7 brane.
So you can define the coercion function in terms of string theory?
Yeah. But it's again a non-perturbative, very strongly coupled string theory, so you can't compute. But in principle, it exists.
So it's not the perturbative string.
Of course, it's not. Otherwise, it would be Lagrangian theory. Yeah.
I see. So you assume that in principle you can calculate the strongly coupled string theory to define.
Or just use this idea of Seiberg duality. Yeah.
Seiberg duality, I don't think it's not a principle. But okay, go ahead.
All right. So in this E6 case too, you can give a var to this field U, and then this breaks this mysterious theory to some U1 gauge theory with massive charged fields. So that's how things are consistent with the mass deformation in the Higgsing. So in fact, you can.
Without Higgsing, that strange sector disappear under that Higgsing.
Well, they just all become massive. Yeah. It's still there. You can see massive fields transforming in E6 representations. So you can even go up higher to E7 theory and E8 theory. This is very easy, and all of them are non-Lagrangian. And you can, each of them has this extra field U, which can Higgs this mysterious theory to U1 theory, like this. So this Minahan-Nishansky, this N theory is, well, a cousin of SU2 with flavors. And you can determine the scaling dimension of this in U in various things. So SU2 with 4 flavors case is semi-classical is superconformal. So U is trace phi squared and its dimension is 2. We determined the dimension of U of E6 theory, that was 3. For the 3 cases with Lagrangian description, you can compute the dimension of U using some other technique. And of course, becoming most strongly coupled in the infrared, the dimension of the operator decreases. So they become 4/3 or 3/2 or 6/5. Instead, if you go down the ladder, go up the ladder, the dimension becomes bigger. So in some sense, it looks like Minahan-Nishansky's theories are less strongly coupled than this SU2 with 4 flavors. As far as the behavior of the scaling dimension of the field U are concerned. So let me conclude by summarizing what I said. So I just want to say that non-Lagrangian theories are everywhere. So when theta is pi, we can start from this Lagrangian system and crank up G to come to this SU2 gauge theory with coupled to non-Lagrangian system. So this is the picture of the moduli space of couplings. So you not only have G, but you have theta, right? So this is 2-dimensional. So this is supposed to be some, sorry for my bad drawing of the pictures, but I'm going to write exactly the same thing. You have something like this. It's really tentacles, 3 tentacles merged in it. So this is supposed to be 2-dimensional. So in this cusp, you have the original SU2NC with G equals weakly coupled case. And this line is the theta 0 line. And on the other side, you have the same theory. Sorry, that's the next slide. And you can go to a strong coupled limit at theta equals pi too. But in the end, if theta is 0, you get exactly the same theory with inverse coupling. But when theta is pi, you get some different theory involving non-Lagrangian theory.
Can you make the G to infinity with non-trivial theta?
Yeah. So what happens can be seen in this picture.
Yeah, in the middle, yeah.
You just
Ah,
go something like this. Yeah. You just have a one-dimensional line in this two-dimensional picture, and eventually absorbed in either of it. Yeah. But that depends on the precise angle of the original line. That's rather complicated. So, what happens when NC is 2? So far, I only talked about NC is 3 or more. In the case of NC equals 2, what happens is that when theta is pi, you get a non-Lagrangian theory at the end, by which I just mean 3 flavors of SU2. Yeah.
Did you take any different NF?
I just take NC is 2 and NF to be 4.
So it's still a conformal.
It's still conformal.
Sorry.
So I can do the same exercise with NC equals 2, and what you get is 1 flavor of SU2 plus 3 flavors of SU2, which is the same with this original one. But the way flavor symmetry acts is different. So this is rotated by SU4 flavor symmetry, but in the end, 3 of the flavors are rotated by SO6 flavor symmetry, and this is rotated by U1. So this is known from 1994, and so what happens is that when the original number of colors is 2, in all of the 3 corners, you just have SU2 with 4 flavors with different coupling constants. So this is called triality, and is given and explained carefully in the paper by Seiberg and Witten. I mean, in the original paper about the Seiberg-Witten theory. So what's important here is that in order to generalize this triality to NC larger than 2, you necessarily run into this corner where you have non-Lagrangian theory. So you just cannot avoid dealing with this stranger cousins of free fields. You can even consider deforming this set of n equals 2 theory by m squared trace phi squared. What in the infrared, what we have is that you add this m squared trace phi squared to this trace q phi q twiddle. So you can integrate out phi. This is the only equation I have today. You can integrate this out, and you get some quadratic interaction of q twiddle. Right? Phi is set to q twiddle. So this means that n equals 1 SUNC with 2 NC flavors, which is the standard example of Seiberg duality, has an exactly marginal quadratic interaction, which can connect 2 ends of the Seiberg duality. Somehow, not many people care about making the coupling constants in the Seiberg's dual pair complex. People usually just are happy with doing with G and M both real, but this means that if you make one of them complex, you can go to the other end where you have an n equals 2 non-Lagrangian matter field coupled to n equals 1 SU2 gauge theory. So this means that the very standard Seiberg dual pair of SCNC with 2 n flavors, which are self-dual, because I mean the dual number of colors is NF minus NC, right? So 2NC minus NC is 2NC. This has another corner in the duality space, which is n equals 1 SU2 pH group with 1 flavor plus a non-Lagrangian matter field. So if you don't consider non-Lagrangian matter fields, you are missing tons of interesting thing about, well, at least supersymmetric gauge theory. So this is the end. The summary is, you just can't say, I don't want to consider non-Lagrangian theory. If you have ever used cyber duality with NC larger than 2, you need to use non-Lagrangian theory. That's it. Thank you.
Any question or comment?
Did people think about the MC larger than 3?
Oh, yeah. It can be done. Well, they are all some strange non-Lagrangian theories. Yeah. Which are all obtained from Gaiotto's TN theory. So, the current understanding, the most general non-Lagrangian theory is so-called Gaiotto's TN theory, from which every non-Lagrangian theory and some free fields can be obtained by mass deformation. So there's a very big one for each n and for each other flavor symmetry.
So you claim that you may define the duration function for that kind of theory, and
Yeah.
it's also possible to define the partition function, for example.
Right. Partition functions, if it's supersymmetric, is much more easy thing to compute.
Is there some explicit example of that?
Well, for Minahan-Milchanski theory, for example, the partition function, supersymmetric partition function of that, of S3 times S1, is no. Yeah, it's completely no. Some expression which is E6 symmetric. For all TN theory, which are more important ones, they are all known.
TN case?
Hmm?
TN case?
Yeah. Rastelli and others are not known. And the partition functions of those Tn guys are given by Macdonald functions or elliptic generalization of Macdonald functions. So they are interesting from a mathematical point of view too.
Any other question?
Celestial four-form field strength in supergravity,
Right.
n dimension.
Right.
That theory is non-Lagrangian in the sense that you must impose the celestial condition.
I won't say that. That is an example where you cannot write down a Lorentz invariant Lagrangian for a system with Lorentz invariant equations of motion. But you still have a Lagrangian there. Yeah.
So any other question? So you don't let them speak again.
Thank you very much.